Okay, class, please let me know if you can see the PowerPoint. Open your mic and tell me if you can see the PowerPoint.
Yes, sir.
Yes, sir.
Thank you,
Cancer.
thank you, thank you, thank you so much. Okay, as I told you, in today's session, I'm going to talk about radiation, the third type or mode of heat transfer. And we will see what is the difference between these type of heat transfer and conduction and convection. If you remember, for conduction, we need to have a substance, a material. Heat should transfer from different component of the substance, from one molecule to the other molecule, actually. From the molecule with higher energy is transferred to the molecule with lower energy. And for convection heat transfer, if you remember, we have some conditions. First of all, we need to have a solid surface. Then we need to have a fluid. It can be liquid or air in contact or in vicinity of the solid surface. And more important thing for the convection, if you remember, is the motion of the fluid. The fluid should be in motion to have a convection heat transfer from surface to the fluid in motion, or from the fluid in motion to the surface, actually, solid surface. And for both of them, we need to have a temperature difference for the heat transfer, to have a heat transfer by conduction or by convection. And also, we have seen equations as before this we have discussed. We have two equations: Fourier law for the conduction and Newton law for convection. Today, we will see also for the radiation. In radiation, the energy here mainly in heat transfer science, as I told you in previous session as well, the energy is thermal energy. So the energy here, which is the definition in the definition of the radiation, as you can see here, means thermal energy actually. The energy emitted by matter in the form of electromagnetic waves or photons. You can see the uh, definition of the radiation is different from conduction and convection. However, this is only the definition of radiation. So the radiation is the energy emitted by matter in the form of the electromagnetic waves or photons. I'm not going the to go to the detail of the electromagnetic waves or photons. Suppose you already know from physics what is electromagnetic wave and what is photon. Simply, you need to know that the, the light which we can see actually, as you know, it includes different kind of the waves and it has wavelengths, and the light is one type of the electromagnetic waves. It has energy, and also from quantum science, you may know that the light or the radiation actually is a combination of its wave and also it is photons. Photon is the pack of the energy, which the radiation can transfer the energy due to the electromagnetic waves or photons. Both of them, both of these two, is called radiation, and the energy can transfer by this. So you can feel that, for example, when the sun is radiating, or you are in the exposed of the sun ray, you can feel the temperature, your temperature of your body or temperature of any surface which receives the radiation of the sun, for example, will increase. This radiation is not only come from sun, and we have radiation from different sources. Any source of radiation like light bulb or any type of the emitting devices actually uh, can produce this radiation energy. Later, you will see that also our body have radiation energy, but it is just reflection. And the radiation which our body produces is infrared actually radiation, and we will go to more detail in the chapter 4, I think, which is about the radiation heat transfer. Here today, I'm just going to briefly tell you how the some basic and some concept of the radiation heat transfer. And to compare the radiation heat transfer with the conduction and convection heat transfer, we can say that radiation is the fastest type of the heat transfer because you can, based on your experience and common sense, you know about that, and the reason is in this type of the heat transfer, the thermal energy is transferred by electromagnetic waves, and the velocity, the speed of the uh, electromagnetic waves is high. For example, you know the speed or velocity of the light, which is about 300,000 meter per second. So the radiation is the fastest type of the heat transfer. Moreover, this type of the heat transfer does not require the presence of the medium. If you remember, for conduction, we need to have a substance. Substance can be solid, liquid, or any type, and the thermal energy is transferred from one molecule to the other one, and we need to have a substance or a medium. And for the convection, if you remember, we had that fluid, the surface, both of them are again some substance or medium. But for radiation, we don't need to have any medium. The simple example is the energy which uh, received by Earth from the sun. Between sun and Earth, there isn't any medium or any substance, but still the radiation energy or thermal energy by radiation is transferred from the sun to the Earth's surface. So this is a good example to show radiation doesn't need any medium. And as you know, again, in heat transfer, we will just study thermal radiation, the radiation which is emitted by bodies because of their temperature. As I said, our body even produce radiation. The radiation, but just the value is much lower than the radiation by a light bulb or the radiation which comes from the sun. But there is a radiation. Anybody will has some kind of the radiation or thermal radiation. And the other important thing about the radiation is the radiation is volumetric phenomenon. What it means? It means the radiation happens from all surface or all volume of a body, and when we study the radiation, we need to encounter whole body surface or body volume. If you remember, for conduction, we had that surface area in the normal to the direction of the heat transfer. For convection, we had that surface area of the solid surface. And for radiation, we assume that, or actually in real world, is the radiation is the volume phenomenon. In whole surface or whole volume of the substance, the radiation is happening. As it is mentioned for solid, liquid, gas, they emit radiation. And also, for radiation, we need to notice uh, any substance emit the radiation, receive the radiation, or observe, receive radiation, and these receive the radiation. Some part of that is absorbed by the substance, and some of that is transmitted. So any substance, all type of the substance emit, absorb, and transmit radiation. This is also important, and you know about that. Later, you will see why it is important. And As I told you, however, we say that the radiation is volumetric phenomenon. Usually, we assume that it is a surface phenomenon for solids, because as you know the liquids, the gases, they are transparent. So we may consider that as a volume phenomenon, the radiation. But for the solids, because we have surface of the solid and the inside of the solid, we don't have radiation, or at least it's not contribute in the heat transfer by radiation. So for solid, we just discuss about the surface of the solid and we calculate the radiation transfer for the surface of. Based on this information and these assumptions which I introduced to you, we have an equation to calculate heat transfer by radiation. The equation is this one actually, Q dot emit. It means the rate of heat transfer by emission or radiation actually. Imagine we have a surface like this, a body like this. I will tell you what is black body, but imagine it is a normal body. Then Q dot emit is the amount of the heat which is radiated or transferred by radiation. The value for normal substances is epsilon sigma AS TS power 4. Epsilon is a property which we call that emissivity. What is emissivity? Emissivity is the ability of surface to emit energy by radiation. Why it is different for substances? You already know about that. You know for example, the black colors, okay, compared to the light colors like white, like yellow. You know, if you put both of these color in the exposed to the same source of the radiation, for example, the black one will the temperature of the black one will increase more compared to the white one. That one is related to these properties, absorptivity. But why the white one, temperature of the white one, increase lower than the black one? The reason is it depends. It's related to the emissivity of the surface. Emissivity of a surface means how much of the light is reflected or transferred by the surface. For the different substances, based on the surface of the substance, especially the color, the emissivity is different. For a substance, an idealized substance, we say that, which we call that black body, epsilon is equal to 1. In other words, it is assumed that the whole surface is emitting radiation. And this emissivity, based on the surface properties, will be different for different substances. You can see here, emissivity of some materials, as you can see, it depends on the temperature of the substances. 300 Kelvin is almost the room temperature. You can see for a material like aluminum foil, the emissivity is 0.07, and you can see for different substances. And as you can see here, black paint and even white paint, you can see the emissivity, how much is different. For different surfaces we have. This table is important, especially in different examples. You see the type of the surface will be given to you, for example. Then to calculate the radiation emitted by that surface, you need to use this emissivity in this equation. So emissivity is important. What is sigma? Sigma is a Stefan Boltzmann constant. It is a constant value, which is determined by experimental works. Sigma is equal to 5 point almost 67 times 10 power negative 8 watt per meter squared uh, uh, times Kelvin power 4. So this is the value of sigma or Stefan Boltzmann constant, which we need to put in this equation. Okay, so this is radiation emitted by real surfaces, and for real surfaces we have different emissivity. But in some special case or special cases or idealized cases, which we will also use in some examples, we can assume that we have a black body. For a black body, sigma is equal to epsilon is equal to 1, or or emissivity is equal to 1. Then the maximum uh, radiation rate of radiation heat transfer is equal to sigma AS TS power 4. In other words, epsilon is 1 in this equation, then this equation becomes this one. Sigma is the Stefan Boltzmann constant, is the surface area of the heat transfer, and as I said, the sorry about the noise, so my office is close to the workshop. AS is the surface of the body, and TS is the temperature of the surface of the body. So we use these two equations. This is the idealized one. This is the actual one to calculate the radiation heat transfer rate. And if the surface is given, simply we can find emissivity here. And for example, we have the temperature of the surface is Kelvin. And please notice this is important when you solve problems. As you can see, temperature of the surface in this equation is in terms of Kelvin. So if the temperature is given, the temperature which is given is Celsius, you need to convert to the Kelvin. And surface area, you can simply calculate based on the geometry of the body or substance. So we have emissivity, which means how much is the emitting or the how much radiation is emitted by the surface. So uh, for sure we can calculate or we can have the absorptivity. How much of this radiation is absorbed? You can see, for example, this is the surface, the radiation is incident to that surface, okay? Some part of these, this much of energy or thermal energy is transferred to the surface, okay? Or reached to the surface. A part of that will be absorbed by surface. So what we have here actually, we can calculate how much of that is absorbed, the radiation heat transfer, how much is absorbed, like this, how much is reflected. It depends on the absorptivity of the surface. So we need to define this absorptivity, which is the ability of surface to absorb the radiation energy. Alpha, similar to the epsilon, is a number between 0 and 1. For a black body, the alpha is equal to 1, or in other words, it absorbs the entire radiation incident on it. So you can see we may have a relationship between alpha and or absorptivity and emissivity. For a substance, usually we have the absorptivity and emissivity are equal. So to calculate the amount of the energy or which is absorbed by the surface, we can use this equation or Kershaw's law, which says the emissivity and absorptivity of a surface at a given temperature and wavelength are equal to this equation. Q dot absorbed amount of the radiation energy which is absorbed by the surface is equal to alpha times Q dot incident. We know, for example, if we know how much is the rate of the transfer by radiation to the surface, Then if we know the alpha for that surface, we can calculate amount of the rate of heat transfer to the surface by radiation for that surface. So this is the amount of energy which reach the surface, Q dot absorb, alpha Q dot incident, and the rest of that is reflected. So if we know how much is absorbed, then we can also have or calculate the uh, reflected radiation or reflected uh, radiation energy or thermal energy by radiation heat transfer. So Q dot reflected is equal to 1 minus Q dot incident. Simply, you can see the relationship that in compare these two equations, you can understand the reason for the calculation. So we have two equations to calculate the absorbed and reflected radiation. Uh, so by this equation, Stefan Boltzmann, you can understand that any surface based on the temperature of that substance is emitting radiation or radiation thermal energy. And any surface also absorb energy, like what you can see here. Q dot absorb, alpha Q dot incident. We can calculate absorbed energy. This is happened all around us, and this is the reason why, for example, when the sun is, the radiation of the sun reach the Earth's surface, even the surfaces which is not directly uh, in the exposed to the sunlight, the temperature of those surfaces also is increased due to the radiation. Because the radiation, when come reach a surface, some of that is absorbed, then will cause the increase in the temperature of that surface, that body. Some of that is reflected, and it will that one will be emitting radiation. That one also will reach the other body, and will be the heat transfer to those bodies, and temperature of those bodies also will increase. So this is the reason which we define these two: radiation, the emitting, and also absorbing the thermal energy. We have this for all surfaces, especially for opaque surfaces. For an opaque surface, we have this. Some of the thermal energy is absorbed, some of that is reflected. But if the surface is not opaque, for example, if you compare glass, okay, with wood, for example, when the radiation heat transfer, if you expose both of them to the sun, radiation of the sun, temperature of the wood will increase more compared to the glass. The reason is the wood is opaque substances and it will absorb more energy. While for the glass, the thermal energy may just transmit through the substance. This is the difference between opaque and the transparent substances. And in chapter 4, as I said, we will discuss more about that. So you have seen we have the radiation, the radiation or emitting radiation, and absorption of the radiation, thermal energy or heat transfer. Then we can conclude that for any surface, we have emitting Q dot emitted. Imagine this is the surface. So we have Q dot emitted and we have Q dot incident or Q dot which reaches to the surface. So the net radiation heat transfer is simply the difference between these two. Some energy come to the surface, some energy go out from the surface. So simply the net radiation heat transfer during this heat transfer process by radiation is difference between these two. The difference between the rates of radiation emitted by the surface and the radiation absorbed is the net radiation heat transfer. And simply we can calculate, imagine, we usually imagine that our surface is covered by a bigger surface like this, which we call that surrounding surface. at which is temperature is T surrounding. This is imaginary surface. In some cases we can have that, but we can imagine in real world. For example, if we have a surface, we can imagine the air also, air in the surrounding, form another surface, which its temperature is temperature of the surrounding. Then the surrounding will emit this amount of the energy to the surface due to its temperature and due to its surface. And the surface which we have, the solid surface, is emitting this much of the radiation heat transfer, or this much of energy is transferred by radiation transfer. So if the temperature of the surface is Ts, temperature of the surrounding is T surrounding, then to calculate the net radiation heat transfer, we can use this equation. Q dot radiation is epsilon sigma As, which is this surface, times Ts power 4, which is the temperature of the surface, T surrounding, which is temperature of the surrounding. As I said, the surrounding is just our assumption. When a surface is completed, enclosed by a large surface at temperature of T surrounding. Simply, we can't have this assumption because normally, generally, the temperature of the surrounding or the environment remain constant. It doesn't change, by seconds, by minutes. It's almost constant. So we can have this assumption, which the temperature of the surrounding is constant at T surrounding. And we assume that the this air or which form the surrounding surface actually, or even some kind of liquid, the body of the air or body of the liquid does not interfere in the heat transfer by radiation. So by these assumptions, then we can use this equation, as I said. And I think all of the parameters in this equation are familiar for you. And this is also important. I think, in previous session, we had an example and there was also a question why we can neglect for internal energy, why we can neglect potential and kinetic energy. And I told you an example about the value of the kinetic and potential energy, which shows the change in the kinetic potential energy in the heat transfer process is almost negligible or very small compared to the change of the internal energy due to the heat transfer. So we can neglect them. Here also, radiation compared to the conduction and convection is significantly higher. Radiation is usually significant relative to the conduction or natural convection, but not to forced convection. So usually the value of the radiation heat transfer is much higher than conduction heat transfer or natural convection. If you remember, we have two types of the convection heat transfer. One of them is natural. We don't use any fan. We do not circulate the liquid by ourselves. It is circulated due to the temperature difference by itself. So compared to the natural convection and conduction, radiation heat transfer is significantly high. But compared to the forced convection, they are almost in same range. This is some extra information for you because sometimes you can even neglect conduction. For example, here in our assumption, we assume that air is not, acting on the heat transfer process, because if you notice, here we have conduction through the air. So, but we can assume that here we don't have any conduction. Why? Because the radiation in this example, imaginary condition, the radiation heat transfer is much higher than the conduction heat transfer or even natural convection, which we have here. So due to this, we can have these assumption, and we can have this equation actually to calculate the net radiation heat transfer for a surface. So here you have seen we can have conduction and radiation. In this case, we could neglect or we can ignore the conduction heat transfer. Then we can write this equation only for radiation heat transfer. Sometimes we may have, imagine we add a fan here, we circulate air here, then we have a forced convection. In that case, for example, then we have a combination. The heat is transferred from this surface to the surrounding by radiation and also by convection or the forced convection actually. So in this case, to calculate the total heat transfer, when we have a solid surface like here and a forced convection heat transfer, for example, then we have heat transfer by two types of the heat transfer method. One of them is radiation, the other one is convection. In that case, the total heat transfer due to the convection plus the radiation will be this one. Q dot total is H combined. You will see what is H combined. AS TS minus T infinity. You already know about AS. A is the surface area of our solid substance. T infinity is the temperature of the surrounding enough far from the surface. If you remember, in the convection, we had these T infinity. So you know what is AS, TS, and T infinity. What is H combined? H, if you remember, is the coefficient for convection heat transfer. Here, because we have radiation, so we need to redefine H. And we call that combined heat transfer coefficient, or H combined, which this H combined actually includes the heat transfer due to the radiation as well. So this H combined should have some kind of the radiation phenomenon in its calculation. As I said, the H combined is here. We will reach that, but this is just simply what I told you. Q dot total is Q dot by convection plus Q dot by radiation, as I said, for this case, equal to H con. So Q dot convection for this example will be equal to H convection, AS ds minus T surrounding. This is convection. You know about that from previous session. And this one, Q dot radiation, we need to use this equation to calculate that. Epsilon sigma AS ds power 4 minus T surrounding power 4, convection and radiation. Then if we combine these two and just keep this AS TS minus T infinity and define H combined like this. H combined is equal to H by H convection plus H into radiation. H convection, which is the properties for the convection, it should be measured experimentally or it should be given. How about H by radiation? This one, we assume that we have a convection due to the radiation actually. This is imaginary amount of H, which is equal to epsilon sigma Ts plus T surrounding times Ts power 2 plus T surrounding power 2. I'm not going to go to the detail for calculation of this equation. If you are interested, you can try or even we can discuss about that later. But simply, you need to know this H combined can be calculated by this equation. Usually Ts is known, T surrounding is known, and epsilon is for the surface. It's if the surface type is given, then you know how much is epsilon. Sigma is constant. H convection maybe sometimes is question which you can calculate. Or it is given, then simply you can calculate H combined to put in our equation and use this equation to calculate heat transfer in this situation, which we have forced convection, for example, or in the question is mentioned, we cannot ignore convection. Convection heat transfer. I hope it is clear for you. And also, as you can see here also, if you notice here, we have we can have simultaneous heat transfer. Here in this example, you have seen that we can have convection and radiation together. We have some combination for the other type of the heat transfer, which is actually the topic for the next session, which is this afternoon. In the afternoon session, we will have go to more detail about the simultaneous heat transfer mechanisms, like combination of the radiation and the convection and so on, and we will see few examples in the afternoon session. So we reach end of this session. Please let me know if you have any question. Class? Class, is there any question? Yes? No question?
No question, sir.
Okay, so you can also later reach me if you have any question about the topic which I have shared with you today in this session. In the afternoon session, as I said, we will go to more detail. Thank you so much for joining to this session. See you after.
Thank you, sir.
Thank
Okay,
you,
thank you,
Thank you,
sir.
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 Thank you, sir.
Thank you.
Welcome.
Thank you, sir.